Imagine plotting an expedition to the most extreme environments accessible to humanity. A continuous 30-minute journey plunging into the darkest corners of the ocean floor, trekking across the hottest places on the Earth's surface, launching off into the vacuum of space to visit the moon, and then taking a rolling trip back again. To pull this off, we have to recognize a strict biological limitation. Our bodies evolved to operate within a highly specific survival band, a very narrow window of atmospheric pressure and moderate temperature. This vertical diagram maps our proposed destinations against those exact biological limits. Drop too far below sea level, and external pressure overpowers the circulatory system. Spike the ambient heat too high, and core body temperatures cross the lethal 104-degree mark. Because we cannot alter human biology to survive these extremes, the entire expedition hinges on the perfection of life support miniaturization. We have to shrink an Earth-like environment down to the size of a vehicle, or even a wearable suit. That engineering challenge begins the moment we leave standard surface elevation. Before reaching orbit, we encounter terrestrial conditions hostile enough to kill an unprotected human in minutes. Survival on this itinerary is strictly a matter of engineering, not endurance. We cannot adapt to these locations. We can only build barriers to isolate ourselves from them. Our first destination is the deep ocean. Down here, the physical weight of the water column pushing down from above generates thousands of pounds of pressure on every single square inch of surface area. This cross-section illustrates how deep-sea vessels prevent immediate implosion. A sphere is the only geometric shape capable of distributing that massive external force equally across its entire surface, preventing any single point of structural failure. Moving from the crushing cold of the ocean floor to the hottest places on the surface, we reach environments like the Danakil Depression. Here, the immediate threat flips from pressure to extreme thermal load. The fatal threshold in these landscapes is the wet bulb limit. This is the specific combination of heat and humidity where human sweat can no longer evaporate. Without evaporation, the body loses its natural cooling mechanism and heat stroke sets in rapidly. To survive prolonged exposure past the wet bulb limit, explorers rely on active cooling systems. They wear garments networked with tiny tubes that constantly circulate chilled liquid, artificially pulling heat away from the skin. By managing the intense pressure of the deep sea and the lethal heat of the desert, engineers developed a working proof of concept. The systems used to survive Earth's extremes laid the exact groundwork required to leave the planet entirely. Leaving the atmosphere requires generating enough energy to hit escape velocity, roughly 25,000 miles per hour, punching through the atmosphere and into a true vacuum. In a vacuum, a human faces an extreme, simultaneous thermal divide. Without air to distribute heat, the side of the body facing away from the sun freezes, while the side in direct sunlight begins to boil. To operate out here, astronauts use the extravehicular mobility unit. This layered, pressurized shell acts as a personal spacecraft, holding a tight pocket of Earth-like atmospheric pressure directly against the skin. Looking closely at the helmet, you'll see a thin layer of gold coating the visor. Gold is highly reflective to infrared light, which shields the astronaut from unfiltered solar radiation and prevents immediate thermal damage to the eyes. Wrapped in this dense package of pressurized, temperature-controlled technology, a human can finally step onto the stark, lifeless surface of the moon. The next phase of this itinerary, tomorrow's expeditions, will push even further into deep space. This requires a shift to fully closed-loop life support, where every single gram of exhaled air and expelled water is captured, filtered, and recycled indefinitely. No matter how far we travel, we remain entirely tethered to our biological constraints. We survive the void solely by carrying a perfect simulation of Earth along with us. Getting to the moon is only half the itinerary. The rolling trip back again presents a completely different mechanical problem. Returning to the atmosphere is usually much more violent than leaving it. To safely reach the surface, a spacecraft has to shed thousands of miles per hour of orbital velocity. It achieves this by slamming into the Earth's atmosphere, using massive air friction to act as a brake. This simulation shows how we survive that friction. By using a blunt, rounded bottom instead of a sharp nose, the capsule pushes the air forward, creating a detached shockwave of superheated plasma that safely distances the most intense heat from the hole itself. To withstand these immense thermal and mechanical loads, the command module requires thick, heavy construction, engineered specifically to endure a few minutes of atmospheric fire. Once the parachutes deploy and the heat dissipates, the expedition finishes exactly where it started, the only location in the known universe where the temperature, pressure, and atmosphere naturally sustain our biology. Plotting a course to the darkest oceanic trenches, the hottest deserts, and the vacuum of space forces us to recognize the extreme fragility of human life outside this specific biosphere. We engineer complex spheres, suits, and capsules to survive environments that would otherwise kill us instantly. But the mastery of these extreme locations ultimately proves one thing. Having the technology to explore the void is a massive feat, but having a perfectly calibrated planet to return to is what keeps us alive.